Intermediate Algebra Jeopardy! Today's contestants include a history major now working in the counseling office, Kyle Neff, an excellent math student from the Germantown campus, Anissa Azizi, and our returning champion, a Montgomery College student from the country of Brazil, Luis Ramos. And the host of Algebra Jeopardy, Bill Witte.
Welcome, players. Let's get right to it. We have some very interesting categories for you today. They are relations, rational expressions, radicals, calculator operations, logarithms, and everybody's favorite, word problems. Now the computer has randomly selected our one lady contestant, Anissa, to go first. So Anissa, the board is yours.
I'll take radicals for 200.
Radicals for 200. The answer is 2 times the square root of 125 simplified. It's you, Anissa.
What is 10 to the square root of 5?
Correct. Now, where did she get that? We can use the product rule to simplify any radical. And basically what we're going to do is we're going to factor whatever's inside it into the good, if you would, perfect squares, and the evil, or leftover trash. In this case, the good, the perfect square root that goes into the square root of 18, is 9, leaving us with a leftover of 2. Now the square root of 9, I know, is 3. And of course the square root of 2 I don't know.
You look marvelous.
And that's it simplified.
Thank you, sir. May I have another?
Now let's look at the one we just did. There's a 2 in front now. We're still going to break our radical 125 into good and evil. But we're not going to forget our buddy 2, okay? The perfect square that goes into 125 is actually 25. That leaves me a leftover
very bad. Definitely unacceptable.
of 5,
Yeah.
okay?
Uh-oh.
Don't forget your 2 for crying out loud.
I meant to do that.
Okay. Now, the square root of 25 is 5, and now he's a number, and 2 will talk to him.
Come on down.
Okay, and 2 can multiply by the 5, and that's where we get 10 square root of 5.
Smoking.
That's the deal.
What have I done to deserve this?
Now, what if I had one with letters? Well, I'm going to do the same thing. It's not that hard. I'm going to break it up into the good or perfect square roots and what's left over. I just do it one at a time. 50, I'll break into what's perfect that goes into 50. 25, leaving me with a leftover.
Oh, shame, shame, shame.
Just a leftover of 2. Now, what's perfect that goes into x to the 3rd? Well, any even exponent is a perfect square. That's going to leave you with x. Now, sometimes they're like your mother. They're all good. And sometimes they're like your little sister. They're all bad.
Whoa! Someone smells stinky.
So sometimes the whole thing goes into bad. Okay? And now that you've done your breakups, take the square root of the perfect squares. I'll get 5x, a to the 3rd, and then I bring down the leftover. And I've taken out every perfect square I can.
Excellent.
And that is the answer.
I don't understand.
Now another approach that you could take to this is to break it into a prime factorization and pull things out in pairs. Remember, any pair is a square. He could come out.
Elvis has left the building.
Now 2 isn't a pair, so he stays in.
Bogus. Oh, what a jip.
And that's the way it stays. Just another approach.
Direction unclear. Please repeat request.
Well, let's do it with this problem. Factor it into prime factor as far as it'll go, and then take out pairs. Okay, well, let's see. There's a pair. He'll come out.
Elvis has left the building.
We have another pair of 5s. He'll come out multiplicatively.
Has left the building.
Have a pair of X's, don't I?
Elvis has left the building.
And that's not a pair.
Bogus.
He goes
Oh,
inside.
what a jip.
Anything that's not a pair
Bogus. Oh, what a jip.
stays inside.
Bogus. Oh, what a jip.
And we multiply.
Is that your final answer?
Well, we multiply 5 times 2x. And you could get it that way too. Okay? Well, let's see. Anissa got that one. So it's back to you, Anissa.
All right, I'll take 400 for calculator operations.
Calculator operations. Okay. The answer is the key used on the calculator to get multiple values of a function. Anybody? Anissa?
What is calc?
That's not correct. Anybody else? No? Okay. We're going to use table. And to get table by going second graph. Okay? That was the one you used.
How about a little fire, Scarecrow?
Now, why would you want to get multiple values of a function? In this case, we have a function here that measures decay of uranium. Okay?
There's something I have to ask you.
And if you wanted to say, well, geez, how long will it take, how much uranium will I have after 50 days? Well, you could put that into the function and have your calculator do it, okay, and you'd get an answer, okay, of 24.6, whatever the units is, okay? But that's just for 50 days. You may want to do it for many different number of days, okay? There's your y equals, there's your x button. There, don't forget where your second button is, okay, and your graph. And don't forget the up. This is going to be of use here, and the down. So if you, don't forget the difference between minus and negative also, okay? Don't forget your old buddy on also. So if you were to turn your calculator on and put in your hit your y equals and clear out what you did before, okay? Then put in the function using the x. Now you could graph it, okay, and cursor to a certain function, or you could go second graph and actually get a table of all the different numbers, and you can use your up and down to go amongst them, okay, for any x value, not just 50. That's the idea, okay? And then you can hit graph and clear to get yourself out if you wanted to see a picture of it.
Thank you, Mr. Know-It-All.
Okay? So whenever you have more than one value that you want to get of a function, use table, which you get by second graph. Okay? Well, nobody got that one, so it's back to you, Anissa.
All right, I'll take 200 for logarithm.
Okay, logarithms. The answer is, this is the logarithm base 8 of 64. Anissa again.
What is 2?
That is correct. Why would the logarithm base 8 of 64 be 2? Consider this exponential equation, y equals b to the x, okay? If we flip everything,
Holy alphabet.
okay, we've got a lot of letters here. Let's change the representation of these letters, okay?
Do you mind telling me what this is all about, Mr.?
Okay, well, I call b the base, okay, and what used to be x is the exponent, and n is the number, okay, if I may.
If you don't start making more sense, we're going to have to put
Well,
you
we
in a
can
hole.
change this around to logarithm language, okay, an exponential like this you may remember. This is that n is the exponent using a base of b. Could be read the log, because that's what logarithms are, logarithm base b of the number n is e. That's another way of writing that equation.
Could it be?
Okay? Logarithms and exponents are the same dad-burn thing, okay? You've got to get used to that. Logarithms are exponents, okay? So either of these equations could represent the same, you know, you could write them the same way.
What a dumb thing to do.
So we could actually rewrite this equation, logarithm base 8 of 64, as 8, which is the base, to the what exponent, because remember, that's what the logarithm is, to what exponent is 64. And what do you have to raise 8 to get 64?
Hey, this is great, man.
Okay, sometimes much easier to write it that way, you see. Okay? Anissa, you're on fire. The board is yours.
All right, I'll take 400 for logarithm.
She likes that logarithms. Okay, the answer is the logarithm base 3 of 1/9. It's Luis.
What is -2?
You are correct. Where would we get a negative with logarithms? Do you remember what negative exponents mean? Because logarithms are exponents. X to the minus a means... What? Well, that's an opposite. Okay, and in that position, it means the multiplicative opposite. Okay, we call the multiplicative opposite the reciprocal.
That's the fact, Jack.
So x to the minus a really means 1 over x to the a.
And now, ladies and gentlemen, let's get ready to rumble.
So the exponent to get from a base of 3 to 1/9, what would we have to do here? We rewrite it. 3 to what power is 1/9? Well, I know 3 to the 2th is 9. I know 3 to the 2th is 9, but I don't want 9. I want 1 over 9. So I need -2. So 3 to the -2, and that was the answer. Okay, remember that negative exponents mean reciprocate. It's you, Luis.
I'll take relations for 200.
Relations for 200. The answer is the set used to replace the independent variable in a relation. It's Kyle.
What is the domain?
Correct, sir. What is that domain again? Remember that the domain in a relation is a bunch of pairs. And the domain is all the first numbers in the pairs. Okay, here's a bunch of relations here. All the first numbers in the pairs is the domain. People say, well, you mean the x's, like in the xy pairs. You're right. All the x's, or we could say the independent variable, because typically in a function you get to pick the x. Okay, and that's the deal. So, Kyle, you're the man. It's up to you.
Relations for 400, please.
Okay, the answer is the set used to replace the dependent variable in a relation. Kyle?
What is the range?
Correct.
I know you are, but what am I?
We remember what the first group was the domain. So all the second numbers is the range. Okay, what you say? Well, the first one were the x's. The range is all the y's.
Frightening.
And the y's depend on the function. You get to pick the x's, but the y's depend on what their value depends on what the function does with them. So that's also sometimes called the dependent variable. Okay, and in fact, let's do a picture here where we might ask you to name the domain and range. Well, let's see. The domain is all the possible x's. What would all the possible x's be? It is a set. Okay, so we'd have set notation.
No problemo.
Okay, let's use our axis here. Well, one of them is 2. One of them is 4. Another x is 6. And in this picture, the last x is 8. Yes! So that's the domain. What would the range be? Is all the possible y's. Well, let's see. Where's the y's? We're going to need... We need the axis here. This is a little tricky. That's going to be a set, so we need our set notation. And we have a 5. Now this is weird. The other one's 5 too.
I know that, dude.
So we don't write it again. And this one's 5 also. We only write the possible y's. So
believe it or not.
Actually, the range in this case is just going to be the set 5.
As always, should you be caught or killed, the secretary will disavow any knowledge of your actions.
This isn't that hard. The domain is going to be all the possible x's. Well, you can go to infinity in both directions. So the domain...
Pay attention, son. This is for your own good.
We know it goes forever because of the arrows. The domain is going to be all real numbers.
Well, ooh-la-dee-da.
If you wanted to be fancy-schmancy, you could write that symbol. That means all real numbers. Now, the range isn't all numbers. It's all the possible y's. And it doesn't go all the way down. Okay, it starts at 0
To infinity and beyond.
and goes to positive infinity. Goes up, but it doesn't go down.
Cool.
Okay, so one way to write that would be as a fancy schmancy. All the y's such that y is greater than or equal to 0. Yet another way to write the range in this case. Okay, well, let's see. Kyle, you're in the lead.
All right, let's keep going with relations for 600.
He likes it.
I do.
The answer is this visually tests if a relation is a function. Kyle's in there first.
What is a vertical line test?
Correct. How do you do that, remember?
To be astonished.
Well, a function, if you actually drew all the pairs, which are points, would come out to a picture. And we want to make sure that something's a function. We want to make sure every x gets only one y, so we can actually...
Excuse me, Professor Brainiac.
Well, we can actually use what's called the vertical line test by drawing a line and moving it across the picture.
Are you pondering what I'm pondering?
Let's try it. As I see, and if it ever meets anything twice, it's not a function. But that only met each point once, so this one is a function. Okay. Gets the function seal of approval.
Thank you, sir. May I have another?
Let's try another example of this. Oh, at this point, you see the vertical line hit 2 points at one place. So that one's not a function. It only takes one pair to screw it up. Hey, what about this one? This is kind of weird. We'll use the vertical line test to see if it ever meets any part of the picture in 2 points. No, I'm not seeing it. Looks like it's okay. So that gets the function seal of approval, and that actually is the sine function, and that's why we call it the sine function.
There's something screwy around here.
What about this one? Let's try the vertical line test to see if it's a function. Well, it's looking good as it goes across. Oh. It only takes one place to meet two, and this one had more than one place where it meets 2 points. So, you know, you only need one to mess it up.
Nothing for you.
So this one's not a function. Okay? So let's see. Kyle, you're way in the lead.
Yep.
What do you say, sir?
Relations for 800, please.
The answer is the inverse of x composed with f of x. It's Luis.
What is x?
You are correct, sir. They undo each other. Remember that the inverse of a function gives you the way back. You say the way back. The way back from what?
I know that, dude.
Well, a function goes from x to y, so the inverse gets you back from y to x.
Whoa!
Okay? Now it has to, if it's going to have an inverse, it has to be a function in the first place because there has to be a way back. Otherwise, it's never coming back.
Pay attention, boys. I'll show you how it's
To
done.
find an inverse, what you do is replace f of x with y, interchange x and y, solve the equation for y, and then replace y with f of inverse of x.
I don't understand.
Well, let's try it. In this case, f of x plus 4, I'm going to replace f of x with y. Then, I'm going to interchange x and y. Then what do I do? Solve the equation for y. You should be good at that over the last 2 semesters. Got to get y alone, so I subtract a 4. Okay? And replace y back with the inverse of x. Inverse of f. Okay? So the inverse of the function, shouldn't surprise you, the inverse of the function x plus 4 is x minus 4. They undo each other.
There's something I have to ask.
How could I prove that? Let's do another one. Find an inverse. Find if the f of x is 3x plus 2, we replace x with y, f of x with y, interchange the 2, now solve for y. It's a little bit more difficult. Subtract 2 from both sides. Let's see, got to divide by 3. And now replace y with inverse function of x. And that means the inverse function of x is x minus 2 over 3. They undo each other.
Woohoo! Come to Papa.
Okay, that's how to find an inverse.
There's something I have to ask.
Now, you know you're right if you compose the two and you get x.
Certainly.
Okay?
And you're going to do it because I said
Let's
so.
try to do it. Let's try to check this. Okay? F composed with f inverse of x. Hopefully, it'll get us back to x. Okay, it's called the composition, or composing f with its inverse. Okay? How do we do that? Take the function inverse, and in every place you see an x, put the original function, which is 3x plus 2. Now we simplify. What happens to the 2's? They're dead, and the 3's can cancel, and look what happened. We got back to x, so we know we have the correct inverse is the deal. Okay?
Say, you're plumb right, Farmer.
Always good to check if you have time on the exam. Okay, let's see. It's going to be to you, Luis.
I'll take logarithms for 600.
And the answer is the log base 25 of 5. It's Anissa.
What is 1/2?
Correct. Where would we get a half?
Not because they are easy, but because they are hard.
Remember that the eighth root, I say the letter A, the eighth root is the same as x to the 1 over a. Okay, it's going to be of use to you on the exam.
Excuse me, Professor Brainiac.
So x to the 1/2 means the square root of x.
I know that, dude.
Okay?
Gee,
We don't put the 2.
Think.
Guess what x to the 1/3 would be? Well, that's going to be the third root. That's why we call it the third root of x. Okay? So these are the exponents that represent these radicals.
Could it be?
Okay? Guess what the fifth, x to the 5th is the same as the 5th root. Okay? So in general, the 8th root of x is going to be x to the 1 over a. So if we want to solve for x here, well, we'd have a base of 25, and we're trying to figure out the exponent. Okay? 5's the answer. We pull our old switcheroo. 25 to what power is 5? Well, I know I have to get the square root of 25, and what power represents the square root is a half, and that's why that's the answer.
Well, this is all very sophisticated.
You could even write it as a decimal if you wanted to look smart. Okay? Okay, Anissa's coming back. What do you say?
All right, I'll take 800 for logarithm.
The answer is, as a single logarithm, 2 log 3 plus 3 log 2, it's Anissa.
What is log 72?
You are correct. How did you get that? Well, we know the properties of logarithms are going to be the same as the properties of exponents, because logarithms are exponents. Remember? So one of the rules of exponents is that when you multiply exponents, multiply numbers with exponents, you add the exponents. So same thing for a log. Another property, since logarithms are exponents, is that when you divide numbers with exponents, you subtract the exponents. Okay, so that's going to be another, since it's a property of exponents, it's going to be a property of logs. Okay, when you divide the numbers, you subtract the logs. So since logarithms are exponents, they have the same properties. Okay, one third property is that when I raise an exponent to an exponent, I actually multiply. Well, that's a property of exponents. So it's going to be the same thing for logarithms. When I raise a logarithm to a power, I actually multiply. Okay, and that's what I'm doing there. I'm multiplying by b rather than raising it to a power. So in this case, what's another way of writing some of these? What's another place where I could put that 2, instead of multiplying, I can put it up there. And of course, 3 to the squared is 9. And what's another place I can put that 3? Put it up there. And remember, when I add exponents, what is the rule? When you add exponents, work backwards. I multiply the numbers. Okay, and 3 squared times 2 to the third is 9 times 8. And as Anissa told us, it is the log of 72.
What a dumb thing to do.
Why would you do that anyway? Well, we're going to call that a contraction, and we're going to use that to solve equations in the future.
Are you pondering what I'm pondering?
For instance, something like this, okay? We can't solve for x, we've got to get rid of all those logs. We have to combine them all into one big fat logarithm. Let's see if we could do it with the log of 2, well, I say 2 logs added is the log of those values multiplied. Okay, let's rewrite this. The base of 2 to the exponent of 1 is x times x minus 1, because that's what the log is, the exponent. So 2 to the 1th is 2, and x times x minus 1 is x squared minus x. Subtract a 2 from both sides, and we've got a quadratic equation. How do you solve that?
Factor, boy.
Let's factor, and remember, a quadratic has 2 answers. You have to decide what makes that equal to 0. There's one answer. And then we have to decide what makes that equal to 0. And those are your 2 answers. Okay? Okay, Anissa, it's back to you.
All right, I'll take 1,000 for logarithm.
She likes logarithms. The answer is log base b of a according to the change of base formula. It's Luis.
What is log a over log b?
You are correct, sir. That's a good
Houston,
formula.
we have a problem.
Okay. When we have other bases that don't work out nicely, consider this could be written, the base b to the logarithm or exponent x equals a. Okay? You're allowed to do anything to both sides of an equation, really, if you think about it, as long as you do the same thing to both sides. So the trick was I took the log of both sides. That seems fair.
I know that, dude.
Okay? Now, if I don't tell you what base here, it's log base 10. Okay?
Come on down!
Okay? Remember the other place what the properties tell us, I can put that x. So log of b to the x is x log b. Well, I want to know what x is. Let me divide both sides by log of b. And son of a gun, x will be
Hey, that's just crazy enough
log
to
of
work.
a over log of b, just as Louise said. Okay, so if you don't know, it doesn't come out exact, okay, you can find something by doing the log of a divided by the log of b. Okay?
That's the fact, Jack!
It's called the change of base formula.
Do you mind telling me what this is all about, mister?
Okay, let's do one using the change of base formula.
I'm afraid I can't do that.
The log of 100, the log base 100 of, let's see, a 10,000.
Hey, that's just crazy enough to work.
You couldn't do it in your head. Couldn't we say
Perhaps I could be of some assistance.
that it's the log base 10 now? This is log base 10 of 10,000 over the log of 100. Now, what exponent do we have to raise 10 to get 10,000? And what exponent do we have to raise 10 to get 100? I think I know both of those.
Excellent.
Okay? The log of 10,000 is 4, and the log of 100 is 2. So I just do the division, and it's not that bad.
How about a little fire, Scarecrow?
Okay, what about solving this one? The log base 6 of 8. I can't put that in my calculator. I don't have the log using base 6 in my calculator. So I use the change of base formula. The log of a over the log of b. Or
Now what am I gonna do?
the log of 8 over the log of 6. Now that I can put into my calculator because I've changed it to base 10 and I have a button for log.
Now I use my secret weapon.
So find out what the log of 8 is, find out what the log of 6 is, do the division,
No problemo.
and you got yourself an answer. You're going to need your calculator, but you can get yourself an answer. Okay, so the only logs you can really get are base 10 unless you use the change of base formula. Okay, Luis, what do you say?
I'll take word problems for 200.
Oh, he dares into the word problems. The first step to any word problem. Looks like Anissa.
What is define the variable?
Correct. If you don't know what you're looking for, you can't do anything. Okay? Always go through these steps. Okay? Always name what X is. And remember, it can only be one thing. If they want to know Susie's and Jim's age, typically let it equal the smaller one. Okay? Once you've named what X is, then name everything else in the problem in X language or in terms of X. Okay? I call those two steps the math to English dictionary. Okay? And I cross out as I go. And usually, once I've crossed everything I've done, whatever's left is the equation. And I write those words in terms of the dictionary. Then I solve the equation. Then I make sure I answer the question.
I want details, and I want them right now.
For instance, in a rate times time equals distance problem.
Excuse me?
Problem like this. We're going to, an additional thing, we're going to use a chart like this. Okay, there's always going to be 6 boxes. Always going to be 6 boxes. And I'm going to tell you to always try and fill in 4 of the 6. Okay? The other 2 are going to be filled in using some formula. Okay? And I call those the hard boxes. And they'll relate in the step 3 or the equation.
Uh-oh.
Okay? Now, what were the formulas we used? Do you remember for rate times time equals distance? Because they'll be on the exam. Distance is rate times time. And if distance is rate times time and you needed to know rate, you could go distance divided by time to get rate. And time would be distance divided by rate. Okay?
Let's play. Here we go.
Okay, here's a typical problem. We have a passenger train traveling at 80 miles an hour and a freight train traveling at 30 miles an hour. It doesn't go as fast because it has to carry a lot of weight. If they travel in opposite directions, the question is asking how long will it take before they are 275 miles apart? Well, let's use our little chart here. We've got our passenger. You always have 2 things moving, our passenger train and our freight train. Okay? What's the first step? Name what X is. What do they want to know? Well, they want to know how long, so they want to know time. And actually, in this case, not always the case,
I know you are, but what am I?
they both travel the same amount of time because they started at the same time and they finished at the same time. Okay? So I actually crossed that out because I'm done with it. Now, what else do I know in terms of X, or what else do I know, period? Well, I know that that one train goes 80 miles an hour. Cross that out. And the freight train goes 30 miles an hour. You cross that out. Now, I have 4 of the 6 boxes, and I fill them in using the formula. And the one that's missing is the box for distance. What is the formula for distance? Well, rate times time. And same the other one. Rate times time. And these 2 will relate to each other in some fashion in the 3rd step, the equation. Well, in this case, the 2 distances...
I'm trying to think, but nothing happens.
Well, let's see. The 2 distances, look at what's left. They travel in opposite directions. The 2 distances have to add up to 275. So the distance the passenger train went plus the distance the freight train went has got to be 275, and you have yourself an equation. Step 4 is to solve that equation. Let's see, we'll add like terms. Solve for X, and X will be 2.5. Now wait a minute.
Going so soon? I wouldn't hear of it. Why, my little party?
We have to do what? We have to answer the question. Is it 2.5 dogs? What did they ask? How long? I think the answer is going to be 2.5 hours. I knew it was hours because the unit that goes in is always the unit that comes out. In this case, I had miles per hour. Okay? Okay, let's see. It's Anissa.
All right, I'll take 400 for word problems.
They're not afraid of word problems. If a painter can finish a house in 7 days, we call this the value of his rate. It's Anissa.
What is 1/7 house per day?
Very good. 1/7. Okay? Okay, let's go back. It's to you again, Anissa.
All right, I'll take 600 for word problems.
Okay. This is the final step to any word problem.
What is answer the question?
You are correct again. It's to you again, Anissa.
I'll take 800 for word problems.
This is the exact length of the hypotenuse of a right triangle with legs 7 and 12.
What
you
is...
couldn't know that. What is it, Anissa?
What is square root of 195?
I think you've got it. How did she get that?
It's always best to start at the beginning.
Remember, a right triangle starts with a right angle.
Ooh, yes.
Okay, 90 degrees. But we represent the 90 with a box, okay?
Fascinating.
And we add another side. Remember what these sides are called? Are the legs, okay? The ones that make up the right angle. And the other side, not the hippopotamus, is the hypotenuse, okay? And the Pythagorean theorem is, for any right triangle, the two legs, a squared plus b squared, the square of the two legs added up equals c squared. Pretty cool.
Pay attention, boys. I'll show you how it's done.
So, of course, Anissa knew to go 7 squared plus 12 squared, and that's got to equal the hypotenuse squared. Well, 7 squared is 49. 12 squared is 144. They add up to 195. So the number squared that equals 195, well, I don't know it.
Now I use my secret weapon.
You could use your calculator and just do the square root on both sides. The square root of something squared, in this case, the square root of 195. And that's an actual, you could actually get a number for that if you wanted to. In this case, it's going to be something in the range of 12.26236. Okay? Okay. It's Anissa again. She's way in the lead.
I'll take 1,000 for word problems.
The final one in the category. The answer is, this is represented by P in this compound interest formula. Looks like you, Anissa.
What is principal?
P represents principal. That's correct. Okay. Okay. Remember what we used this for when we figured out compound interest for banks. Okay.
It's mine, you understand? Mine.
A was the total amount that you accrued. P was the original principal that you put in when you were saving. R was the rate, the interest rate that you put it in for. T was the time that you put it in for. And N was how often you, the number of periods, or how many years, okay?
Now what am I gonna do?
For instance, we might ask you on the exam, how much would an investor accrue? How much would they have at the end after investing $500 at an interest rate of 7% for 4 years when you compound it monthly, okay? Well, let's see. Note that we put in 500 for the principal, 12 came from the idea that it was compounded monthly. That means N is going to be 12. The 0.07 is the interest rate, 7%, written as a decimal, okay? And the duration in time is 4 years, okay? And you can actually put that into your calculator, okay? Good old calculator. Don't forget that for the exam. Okay, and if you type that just that way, you got to use those parentheses. Note how important these parentheses are here, okay? Because I want to raise it to that full power. I don't want to just raise it to the 12th power, get an answer, and then multiply by 4, okay? I want to raise it to, actually, to the 48th power, okay?
Oh, it didn't work.
Okay, be careful with the parentheses. That's the most common mistake people make on the exam.
Show me the money!
And that's what you would have. And that's a reasonable amount of money to have, okay? Certainly you wouldn't want to have less money, would you? Okay, you put in 500, so you should have more, and that's a reasonable amount. And I hope you'll ask that for all the word problems on the final exam. Is that a reasonable answer?
Do that again.
Okay, now this one's going to ask, how much would you accrue after investing $3,000 at a rate of 10% for 5 years, compounded quarterly? Well, the only hard part is what's the magic number for quarterly? It's going to be 4. Once again, I can put that into my calculator.
Now I use my secret weapon.
Be careful with the parentheses, okay?
Warning, warning, warning.
Parentheses are critical here.
Mine.
And you'll have, at that point, you'll have, well, you had a pretty good interest rate there. You had 10%. So after that 5 years, you're going to have 4,915 and some change. Okay? Okay, Anissa. She likes anything with money. It's up to you.
I'll take 200 for calculator operations.
Calculator operations. 400. No, we already had 200, I'm sorry. The answer is, other than the on button, this is the first key used to graph a function. It's Anissa.
What is y equals?
Very good. That's why you always have to solve for y, because you got to use that y equals button.
Now I use my secret weapon.
Okay? Note that y equals is the very first button in a graphing calculator. That's why we call it a graphing calculator. Okay? There's the X button, the graph button, the clear button. That's what you're going to use to erase stuff. Okay? Don't forget that's the negative button and that's the minus button. They're different. Okay? And of course your old buddy, the on button. Okay? Now, you might use the second button.
And now, ladies and gentlemen, let's get ready to rumble!
If I asked you to graph this using a graphing calculator, actually the first step you would have to do, you'd have to solve for y first. I don't want to, that button doesn't say 5y plus 2x equals. It says y equals. So we have to get y by itself. Trust me, if I subtract 2x from both sides and divide by 5, subtract 2x from both sides, and then divide by 5, okay, now I have something I can put into the calculator.
I know you are, but what am I?
Okay, so I hit y equals, hit on, then I hit y equals, then I actually type negative 2x divided by 5 plus 3. Now that's the negative, okay? Oh, I have to clear out, I forgot. I have to clear out first. There might be something in there. Then I type it, and then guess what you have to do to hit graph, to graph it?
Woohoo! Come to Papa!
Just hit the graph button, and there's your picture, okay? That's going to be of great use to you on the exam. If you want to get rid of the picture, clear it out, okay? Okay, Anissa, what do you say?
I'll take 600 for calculator operations.
He likes that calculator. The answer is one of the two buttons used to adjust the view on your calculator. One of the two buttons used to adjust the view on your calculator. Nobody's getting it? Oh, it's Anissa.
What is zoom or window?
Boy, you're pretty good. You're correct. It is zoom or window.
Hey, man, check it out.
You can't hit that button too early, players. Okay?
Ooh, yes.
How do we use those? Okay? If I were to try and graph that, okay, I'd hit my on button. I'd hit y equals. I'd clear out the old work, and then I'd type in the function. Okay? Now that's a cubic. 0.5x to the third plus 12. And if I hit graph, I think you'd be disappointed. Okay? But it's not going to look like a cubic. Because you know why? Because you're in too close. So one of the things you can do...
Oh, it didn't work.
Well, it worked. It's just that you're in too close.
Well, why don't you fix it, meathead, huh?
Well, we can do that. Okay? Use your buddy's zoom. Okay? So I actually hit the zoom button. And in this case, I would either cursor to zoom out or hit the number 3, and it would zoom out. I have to hit enter because it wants to know if I'm either hit 3 or move down to 3 and hit enter.
You look marvelous.
And you see that the picture changes, and it does look like a cubic. Remember that a cubic changes sign.
Now look at, I say look at here.
Okay, here's some of the useful zooms that are in the list, though. Okay, you can zoom to a box. You can actually pick the picture that you want it to, you know, the left and right margins and top and bottom margins. Okay, you can zoom in or you can zoom out. I think you're going to use zoom out most often myself. Or just go back to the normal schmormal zoom standard. Okay?
And now, ladies and gentlemen, for our next
now if we tried to do this one, graph this, once again we turn it on if we need to, hit y equals, clear out the old one, and type in your function. Now if you hit graph and you didn't like it, Okay, this time I don't see anything. It's there, I just don't see it.
What happened?
Well, I think in this case I'm too low. I'm looking down, okay?
Now I use my secret weapon!
Well, I can use window and change kind of the side, change the margins to where I'm looking, okay? If I hit the window button, you see where it is, and I got to go down, down, down to set the minimum, okay? The minimum is the third one down, and I'm going to set the minimum from what it is to a lower number. So I'll be looking, I'm sorry, I'm looking higher. I want to set it to a higher number, okay? And perhaps change the maximum value to 50. So I'm looking between those two numbers, okay, rather than the standard, because that's where my picture was. Now if I hit graph, I can see the picture, okay? And the dots that you see, you're used to seeing the axis. The lines are dotted because they're not really the axis. They're your margins, okay? So, what are some useful window settings? Well, the X-min is going to set the left margin. The X-max is going to set the right margin. The X-scale, the Y-scale, the Y-max is going to set the top, and the Y-scale is going to set the Y-scale, obviously. Okay? Let's see. It's going to be Anissa.
All right, I'll take 800 for calculator operations.
Calculator operations. The answer is the key sequence, the keys that you would hit to produce a square root sign on your calculator. You can't just hit square root. It's Luis.
What is second x squared?
You are correct, because there's a button for x squared, but to get to the square root,
now I use my secret weapon.
You're going to have to hit, there's the x squared, and there's the second. And anything that's orange, remember, you're going to have to hit second to get it.
I know that, dude.
Okay? And probably after you hit the number, you're going to have to hit enter. Okay? So if you turn that thing on, if you hit second x squared, that gets you the square root sign, and then type in some number perhaps, whatever it is, 16 we'll say. Now you're going to have to hit enter, okay? Because it needs to know you're done typing the number.
Ooh, yes.
And it actually gives you the answer. Okay, in this case it's going to give you a 4. It can only give you one answer. It's not going to give you that negative 4. Now if I wanted to see if I was right, if I took that and hit x squared, it would square the 4 and get me back to my original 16. Okay? Not too bad.
How about a little fire?
Now some of them aren't exact, of course. That's why you use your calculator, okay? So we wouldn't need to hit on again. Okay, and if we hit second x squared, we get our square root sign. Now put in 14. Well, 14 is not going to come out even. Okay, I suspect it's going to be less than 4 because the square root of 16 is 4. Okay, so I get square root of 14. I hit my enter, and it gives me an answer. Well, it's an approximation, mind you. Remember, it's not exact. These non-exact square roots really go on forever, as you know. Okay? And if we square it, weirdly enough, probably it's going to come back to 14.
Surprise, surprise,
Now, I was surprised at that, but remember, the calculator, while it's giving you an estimation for the square root, it's also giving you an estimation for the square. So 14 is an estimation as well. So don't be thinking that those crazy numbers, that's crazy number that's the square root of 14, is an exact answer. It's pretty close because it's to like the 10,000th. So that's good enough for government work, okay?
What happened?
Okay, let's see. Luis, I guess it's you.
Rational expressions for 200, please.
You guys are afraid of fractions, aren't you? This is used to simplify complex fractions. Kyle's in there.
What is the lowest common denominator?
You are the man. LCD. That's correct. How would you do that for complex fractions? Look at these nightmares.
Holy alphabet.
Well, we're going to find
There's something I have to ask.
the least common denominator of all the fractions in this fraction. Well, let's see. I've got a fraction with an x denominator and a fraction with a y denominator.
Certainly.
So the LCD in this case is going to be xy. He's going to be your superhero. If if you multiply everybody, now you got to be fair, you got to do it to everybody. Everybody by xy, why can you do that? If you do it the top and bottom, you're really multiplying by your buddy 1.
LCD
Anything over itself is 1, okay? So let's do it.
LCD man.
Do him.
Played it for her, you play it for me. Play it for me.
Got to do it for everybody. Let's see what we get. Well, let's see. In the top, I get 5xy. I like that because there's no fraction. Here, the x's are going to cancel, and I get y times 1.
Come on down.
That's sweet. Here, the y's are going to cancel, and I get x.
Come on down.
And I've simplified this complex fraction. It's no longer a fraction in a fraction.
No problemo.
Okay?
The important thing is it your final answer?
Can I cancel things that are added? Oh. Don't ever do that. That's the most common mistake. You can't cancel things that are added. Sometimes you just have to leave it the way it is. Okay? Okay, Kyle, you're coming back.
Let's finish off relations for 1,000.
Okay. The only type of function that has an inverse. Louise is in there.
One-to-one function.
Correct, a one-to-one function.
I'm trying to think, but nothing happens.
Okay, the special type of function called a one-to-one function.
Excuse me?
What makes something one-to-one? Well, if every element in the domain is paired with only one element in the range, you say, boring. Well, that's what makes it a function. What makes it a one-to-one function? It's if it works both ways, if every element in the range is paired with only one element in the domain. Okay? If every x gets only one y and every y gets only one x.
Excuse me?
Okay? The easiest way, I think, is if all the x's are different and all the y's are different, you'll have a one-to-one function. Okay? But it only takes one pair to mess it up. Okay?
Prepare to be astonished.
Now remember that we had the vertical line test to test a function. Okay? We can test whether a function is one-to-one by first we have to test to see if it's a function using the vertical line test. And this is a function. But then additionally, to be a special function, a one-to-one, we test to see if it's a one-to-one using a horizontal line test. And this one is a one-to-one function.
Uh-oh.
Is this one a one-to-one? Well, we'll use the vertical line test.
Your story is very compelling.
Wait a minute.
Is it a one-to-one function?
Uh-oh.
It only takes one to mess it up. Okay? That one is a function, but it's not one-to-one. So we can't take its inverse.
Oh, very bad. Definitely unacceptable.
Okay?
Yeah.
Okay, Luis, it's to you.
Rational expressions for 1,000, please.
1,000. Used to add fractions with different denominators. Anissa.
What is the least common denominator?
You are correct. You love the least common denominator. We use it for everything. For instance, to add these two fractions, we can't add them if they have different denominators. Okay? So we have to find the least common denominator. The least common denominator of 7a and 6a will be 42a. Okay? And then I say to myself, what did I do to 7a to get 42a? I said, well, I multiplied by 6. So 15 says, hey, what about me, bub? I need a 6 too. And in effect, you're not breaking any rules because you're multiplying by your buddy 1, which you can do anytime you want. Now in the bottom, I multiplied 6a by 7 to get 42. So I have to multiply 8 by 7. Once again, in effect, I'm multiplying by 1, so everything's hunky-dinky. Well, now I've got two fractions that have the same bottom.
Is that your final answer?
And I can add the 90 and the 56 and get 146. But don't forget, with fractions, you always have to give the answer in lowest terms. Okay?
Do that again.
Let's do a little bit more difficult. In this case, our least common denominator, I need one of everything, kind of.
LCD man.
So I'll need 15 from the 3 and the 5. I'll need x squared, and I'll need a y. So what did I do to go from 3x squared to 15x squared y? In other words, who's new? Well, 5y. So 2 says, I need a 5y. Okay? And in the bottom, of course, that 5y over 5y is your buddy 1. In the bottom, the new guy, if you would, is 3x squared. Okay? You could use division to get that, if you would. Got to do it to the top also. Whatever you do to the bottom, you have to do to the top, so you're multiplying by 1. Okay? Well, now all we have to do is add the tops. We can't add the tops, and we can't cancel. So we're done. We have the answer. Okay? Well, it looks like we've run out of time at this point. Let's see what we have. We have Kyle in third with 1,400, Luis with 4,000, and in first place so far is Anissa with 6,200. Now I hope, this is Professor Witte, I hope you'll be back next time for the rest of the game. We'll see you then.